Okay, as we saw in when we were dealing with frames of reference, things like velocity are relative to basically to whatever your frame of reference is. So you can pick one frame of reference and you get one answer for velocity. You could pick a different frame of reference and get another answer for velocity for the same object traveling at the same overall velocity. And so, you can choose an external frame of reference. And in many cases, there's more than one external frame of reference that you can choose. Or in some cases, you can choose an internal frame of reference that is related to something within the system. Now, if velocity is relative to your frame of reference, that would imply that kinetic energy must also be relative to your frame of reference, because kinetic energy is 1/2 mass times velocity squared. So there's velocity in there. So kinetic energy is also related to your frame of reference. And it can change depending on what the frame of reference is. And a good example of working out problems like that is example 7.7, where you try to find your kinetic energy relative to different frames. Here we have a 75-kilogram person walking down the center aisle of a train at a speed of 1.5 meters per second relative to the car, relative to the train car. And the train itself is moving at 15 meters per second relative to the tracks, which are, of course, affixed to the ground. So the question is, what is the person's kinetic energy relative to the train? Well, they're moving at 1.50 meters per second relative to the train. So that's the velocity we would use for their kinetic energy relative to the train. So K is 1/2 mv squared. That's 1/2 75 times 1.5 squared. And that's 84.4 joules, just joules. Okay, now what is the person's kinetic energy relative to the tracks? Now, relative to the tracks, there are actually two possibilities here, because it says the person's walking down the center aisle of the train car, and there might be certain connotations to that, but it's not clearly stated whether walking down the aisle means toward the front of the train or toward the back of the train. Or in other words, we don't know whether the person is walking in the same direction as the train is moving, or in the opposite direction in which the train is moving. So if that's not stated explicitly, that means there are actually two possibilities. One possibility would be the person's walking in the same direction as the train, in which case the person's velocity should be added to the train's velocity, because the train is going 15 meters per second forward and the person is going 1.5 meters per second in addition to that. So relative to the ground, or the tracks in this case, the person's kinetic energy, in that case, if they're walking toward the front of the train, would be 1/2 75 times 15 plus 1.5 squared, or 10,209, or 10.2 kilojoules. On the other hand, it's possible, depending on how you understand the word down, or the phrase down the aisle, it's possible the person could be heading toward the back of the train, or in other words, walking in the direction opposite to the movement of the train. And in that case, it would be 1/2 75 times 15 minus 1.5 squared. And that would be 6834 joules, or 6.83 kilojoules. So those are the two possibilities. If I give you a question like that on a test or a quiz, I will try to be more explicit about which direction the person is headed than this problem was. Or at least maybe I'll clue you in that there are two possibilities if I want to be vague about which direction they're heading in. Okay, so the next question is, what is the person's kinetic energy relative to a frame moving with the person? That might seem, it might seem obvious at first, and then you might say, no, it couldn't be that. That's too obvious. But actually, it is that obvious. If the frame of reference moves with you, then your kinetic energy relative to yourself is nothing. And indeed, it's zero. Because your velocity relative to yourself is zero. Because, relative to yourself, you're not moving. And so the KE would be 1/2 75 times 0 squared, which is 0. So if the frame of reference is attached to you, and that means that your velocity and your kinetic energy relative to the frame of reference, which is you, would be 0. So there are all kinds of different frames of reference. Like I said, we saw here relative to the train, relative to the tracks, relative to something that's moving along with you, like relative to yourself. And there are other possibilities as well. I mean, because, really, we think of taking the frame of reference as being the ground, as being a frame of reference of something that's not moving. But in fact, of course, the ground is moving. The Earth is moving. The Earth rotates on its axis and it revolves around the sun. And our solar system is moving relative to the rest of the galaxy, and our galaxy is moving relative to the rest of the universe. So really, nothing sits still in absolute terms. It's all relative. So from our point of view, it appears that the Earth is sitting still, and therefore we often use the Earth as a reference point that's relatively constant. The kinetic energy of an object cannot be negative, and that's simply because mass cannot be negative, and v squared cannot be negative either. Velocity can be squared, velocity can be negative, but when you square it, it's got to be positive, because a negative number squared is positive, and a positive number squared is positive. So kinetic energy is always positive. If you get a negative answer in working out kinetic energy on a question, there's definitely something wrong. The kinetic energy of a system of particles can actually be made up of several different types of kinetic energy. The kinetic energy of something moving from one place to another is called translational kinetic energy. So like the person walking down the aisle on the train, that's translational kinetic energy. The train moving on the tracks is also translational kinetic energy. There's also rotational kinetic energy. That is something that's rotating, like say the Earth on its axis would have rotational kinetic energy because of that. We didn't do the sections on circular motion, so we won't really encounter that, but it's nice to know that it exists. There's also vibrational kinetic energy, which can be either something that's vibrating because of thermal energy, like molecules that vibrate in place, or a spring. If a spring is vibrating back and forth, that could be vibrational kinetic energy. And there's internal kinetic energy if the frame of reference is internal. There's also thermal kinetic energy, which is the kind of kinetic energy, whereas vibrational kinetic energy can be caused by heat. That is, heat will cause molecules in a sample to vibrate back and forth, and the more heat they get, the more, the faster they vibrate. That's considered vibrational kinetic energy. Thermal kinetic energy takes the form of random molecular motions. The fact that, say in a gas, the individual particles that make up the gas are zipping all over the place in random directions at high rates of speed until they hit something, and then they bounce off and zip in another direction at a high rate of speed. That's because of heat or thermal energy that gets the particles moving. And so that would be thermal energy. And in fact, temperature is related to that, because temperature is just a measure of the average kinetic energy of the particles in a sample or an object. And so the more the sample heats up, the more thermal energy the particles have, and the higher the temperature becomes. Okay, looking into some of these types of kinetic energy, we can look at the next example, which is in a basketball game, a player lobs a pass with a 624 gram ball, which I've written in as 0.624 kilograms, which covers 15 meters in 2 seconds. What is the ball's horizontal translational kinetic energy? And again, translational kinetic energy is just the kinetic energy of something that's moving from one place to another. And it could be in a straight line, it could be in a curved line, but it involves movement from one location to another. So if we're going to find kinetic energy, we need 1/2 mv squared. We have the mass of the ball, but we don't have the velocity. But the question does tell us that it covers 15 meters in 2 seconds. So 15 divided by 2 is 7.5 meters per second. So there we go. There's your velocity. So 1/2 0.624 kilograms times 7.5 meters per second, the quantity squared, is 17.6 joules. That's the translational kinetic energy of the ball. In addition to that, the molecules that make up the air that's inside the ball have a certain amount of kinetic energy also, because they're zipping around inside the ball. And their motion is more or less independent of the direction of the ball. They're moving around simply because of the heat energy that's present within the ball. And they're moving around because, well, also because not only of the heat energy, but because the molecules are very small and they're very light. And also because there's no attraction between them. So there's nothing to get them to stick together. They're just very free moving in any direction. It says here, the average molecule of air inside a basketball. Now that right there, I put in quotation marks because of course air, well, this not being chemistry, we didn't really cover this, but air is not a pure substance. Air is a mixture of different substances. The air we breathe here on Earth is mostly made up of nitrogen, something like 79% nitrogen, and about 23% oxygen, and then fractions of a percent of things like carbon dioxide and water vapor and things like that. So an average molecule of air just means basically a molecule with a weighted average mass of nitrogen and oxygen and carbon dioxide and water vapor, weighted for the percentages that they make up in the air. And so that's what they mean when they say the average molecule of air has a mass of 29 U, which again, not being chemistry, we didn't cover this, so I don't know why they're throwing this in. But 29 U is also known as 29 atomic mass units. An atomic mass unit is just a unit that's assigned, that gives you convenient numbers for the masses of atoms. Say 1 proton would be about 1 atomic mass unit. 1 neutron is about 1 atomic mass unit. And electrons, as it turns out, are so small that we don't even count them towards the mass of the atom. So 29 atomic mass units just means that the average molecule that makes up air would contain a combination of 29 protons and neutrons. We don't know how many of each, but we don't really need to. There are just 29 of them altogether. And that's 29 atomic mass units. And there are ways that we can take that number and find out what the mass is in kilograms. And we'll get to that in a minute. But first, let's go on to the rest of the question. The average speed of these molecules is 500 meters per second. That's really fast. But again, like I said, they're really small and there's no attraction between them. So there's nothing holding them back. And that's why they move so fast. There are about 3 times 10 to the 23rd molecules of air inside the ball. That means, you know, when you take up the total of all of the molecules of nitrogen and oxygen and carbon dioxide and water vapor, the total would be about 3 times 10 to the 23rd power, which is a large, large number of molecules. But, you know, again, molecules are really, really, really small. So you can fit a lot of them in a given space. And even so, even with that large a number of the molecules of air present, they're still pretty far apart relative to their own sizes. So there's not only, molecules are so small that there is room for this many of them inside a basketball, and they can still be far apart from each other. And they're moving in random directions. Because again, there's no attraction between them, so there's nothing holding them back. They just move in a random direction until they hit something, and then they bounce off and they move in a straight line until they hit something else, and it goes on like that, and on and on. So what we want to know is, what is the average translational kinetic energy of the random motions of all of the molecules inside relative to the ball? So in other words, what we're going to have to do is find out the kinetic energy of one of these molecules and multiply it by the number of molecules. So that's really all we have to do. And that is equivalent to taking the sum of all of the kinetic energy of all of the molecules in the ball. So first of all, back to the mass. They tell us that the mass of a molecule of air is 29 atomic mass units per molecule. And you can look up a conversion factor between atomic mass units and kilograms if you want to do it the easy way, the physicist's way of doing it. One atomic mass unit is 1.66 times 10 to the minus 27 kilograms. Or you can do it the chemistry way. And actually, since this is not a chemistry class, I'm really not going to go into detail on this. We'll just say that you end up with the same result either way. And that is 4.82 times 10 to the minus 26 kilograms for a mass of the average molecule that makes up air. That's what comes out of all of this. That's the important part. Kinetic energy is, although actually I will go into detail on using the conversion factor that oh, that's 29. I will go into detail on how to do it using the conversion factor there. That is, once you know that one atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms, it's just a matter of multiplying that by the number of atomic mass units you've got. So it's 29U times the fact that there's 1.66 times 10 to the minus 27 kilograms for every one U. And when you multiply that together, you should get, all right, 29 times 1.66 times 10 to the minus 27 equals, syntax error. Okay, try it again. 4.814 times 10 to the minus, I'm getting a shadow here, 26. Okay, and that is 4.8, yeah, well, 4.82, 4.81, close enough. That's what I got here. Okay, kinetic energy is 1/2 mv squared. So we've got the mass in kilograms per molecule times the speed in meters per second squared. And we get 6.03 times 10 to the minus 21 joules per molecule, which means the total kinetic energy is just going to be the number of joules per molecule times the number of molecules. So that's that times 3 times 10 to the 23rd molecules, and that gives 1,808 joules. And that is the internal kinetic energy of the ball. Okay, so then the question is, how fast would the ball have to travel relative to the court, or relative to the ground, as we were working on in part A, in order to have the same kinetic energy as the total kinetic energy of all of the molecules in the ball, as in part B. So in other words, how fast would you have to throw the ball for it to have that much kinetic energy, 1,808 joules? And so if kinetic energy is 1/2 mv squared, you can solve that for velocity. Okay, so if you want to solve for velocity, first you have to get velocity alone. So we would want to divide both sides by 1/2, but that's the same as multiplying by 2, and that cancels out the 1/2. Then we want to divide both sides by m, which cancels out m on the right-hand side. And since that gives us v squared, if we take the square root, we will get v. And so sure enough, v is 2 times the kinetic energy over the mass. Okay, so then velocity would be 2 times 1808 joules over 0.624 kilograms. That's a K that's all smudged up there. And that equals 76.1 meters per second. So that's quite a bit faster than the player actually threw it. That's probably faster than any player could throw it. Maybe a baseball, maybe, but not in basketball. Okay, I think that's about enough for this segment. So I'll cut it there and we'll come back in a moment with the rest of today's proceedings.